Hi, everybody. So you see the notes are written up. That's because I accidentally recorded it without the voice. I thought instead of erasing it, let's just go over it. It's already written for you. So we have the mass of an object with variable density, rho xy, is given by m equals the integral over the region of rho of xy. Okay, it's pretty self-explanatory, I would think. Just integrate the density to get the mass. Now, moments about the x and y axis. I like to think of this as a torque. Okay, thinking about it as a torque reminds me that, oh yeah, it's about how it's rotating about the given axis. So the rotation around x is governed by the distance y from the axis of rotation. Okay, so that's how you get this expression. mx equals the integral of y rho of xy dA. Similarly, the moment about the y-axis. Okay, about the y-axis, the rotation around the y-axis, or the torque, is governed by that distance x from the y-axis. Okay, so that's how the x comes in here into play. All right, so the moment about the y-axis is the integral over the region of x times the density with dA. All right, center of mass. Okay, the center of mass, x bar, y bar. Now, x bar equals the my over m. Little confusing, but how I remember it, is that x bar, when I do the integral, should have the x in it. Okay, so if it has the x in it, then it's going to be this m sub y. Similarly, y bar, when you do the integral in the numerator, it's going to have the y in it. So that's going to be, I know, m sub x. It's not a great system, but it's what I got. Okay, so center of mass is then, don't have to do much. Okay, don't have to do much once you've done the integrals from the moments of inertia, but it's just remembering which one's which. Now, one thing to keep in mind about center of mass: if you have an axis of symmetry, center of mass is on it. Okay, so if you have, for symmetric problems, or problems that have some sort of symmetry, you can reduce the center of mass significantly, what calculations you have to do. Okay? Finally, moments of inertia. So moments of inertia have to do with how it's rotating. I'm right at this moment, I can't remember exactly what they mean, but they do signify something. It has to do with angular momentum. But let's just calculate it. To calculate it, the moment of inertia about the x-axis is just y squared rho xy. So just like m sub x had y in it, I sub x is going to have y squared in it. Okay? Just like I sub y had x in it, m sub y had x in it, I sub y is going to have x squared in it. And then you also have this polar moment of inertia. Okay. All right. I actually like how this went, so I think I'm going to try it again with the next one. We'll see how it goes. Give me your feedback if you like it better when I write while I'm talking, or if I write first and talk later.